Alright, so this is part 1 of alternating current. This video is going to serve as a bit of an intro for our alternating current videos. We're going to mix it in with a few concepts that we already know, such as induction and Faraday's law, and we'll get a sense of why the electricity that we generally use is alternating current rather than direct current, which is DC. And that has to do with how generators are made, and that most of them have to have alternating current as a consequence. So we call alternating current AC, okay? And obviously the A stands for alternating, okay, and the C stands for current. Okay, so this is opposed to DC, which obviously the D in that stands for direct, and obviously the C still stands for current, okay? So AC, alternating current. So a way in which we can generate a current and therefore generating electricity is by inducing a voltage. And we know that in order to induce a voltage, Faraday's law applies, right? And we know in order for Faraday's law to work, we need a rate of change of flux, alright? So the way in which we generate electricity through Faraday's law is through what's called a generator, okay? And essentially what a generator is a motor in reverse, okay? So typically when we have a motor, we would have a magnet right here, okay? So this, we could say this is the North Pole, and then we'll have another magnet right here. And this is typically the South Pole, okay? And then we'll have a coil in the middle. And if we were to put a current through this coil, okay, like so, through Faraday's left-hand rule, we can see that the coil is going to rotate like so. Okay? And so therefore we have converted electrical energy into mechanical energy through the rotation of this coil. So that is a motor. A generator is the opposite situation. In a generator, we would rotate the coil, okay? And then as the coil interferes with the magnetic field generated by these permanent magnets, a current will be induced into that coil. Okay? So you see how a generator is just the opposite of a motor. In a motor, we put a current through the coil, and then that causes the coil to rotate. But in a generator, we rotate the coil, and that induces a voltage and therefore produces a current within the coil, therefore converting mechanical energy into electrical energy. Okay, so based on that concept, if we were to have our generator once more over here, so we have our North Pole here and our South Pole here, and we have our coil in the middle, okay? If we were to draw our magnetic field lines from north to south, okay, we can see how this coil is parallel to the magnetic field. And so because of that, we should have learned from our level 2 that when our coil is parallel to our magnetic field, there will therefore be no flux, okay? However, if we take this exact situation, and now we rotate our coil by 90 degrees, okay, so we've rotated it this way, by 90 degrees, okay, you've seen here. In this situation, it's flat, and then we rotate it by 90 degrees, and now it's up and down. And so as you can see, this coil is now perpendicular to the field lines. And so at this case, the coil is perpendicular to our magnetic field. Therefore, this is max flux. Now, it's important to note that the max and no flux is not really important for inducing a voltage, because if we remember our Faraday's law is concerned with the rate of change of flux, okay? So as we rotate this coil, okay, so we first rotate the coil, and remember we rotate the coil through some sort of mechanical means, like for example, we might have steam pushing a turbine or water pushing a turbine. That's what happens in a dam. Steam usually happens in like a coal plant or a nuclear power plant. Or we could have wind pushing a turbine, and that's what happens with wind turbines, okay? So we rotate the coil through some kind of mechanical means, okay? This results in a change in flux through the coil, okay? So as you can see, as we rotate this coil, we went from no flux to max flux, and therefore there is a change in the flux over a given period of time, okay? And so therefore, due to Faraday's law, this will induce an EMF, and therefore a current will be produced within the coil, okay? And that is due to our Faraday's law. And so because we're concerned with the rate of change of flux, to find out where the rate of change of flux is at a max versus where it is at a minimum, I will propose we look at the coil from this point of view, okay? So if we imagine we have our magnets right here, so this is our north and this is our south, okay? And then we have two circles right here, okay? So imagine these two circles are either these wires or these wires, okay? It doesn't really matter. Let's imagine it that these circles are these two wires right here, okay? So this one would be this side right here, and this side will be this side right here, okay? So imagine we're looking at it from this point of view, okay? And we can draw this back part over here, so it makes it easier to visualize. As this coil rotates, it's going to rotate like so, okay? And so therefore, initially, there is no flux, okay? And so that is what we determined up here, okay? However, the rate of change of flux is at a max, okay? And we know this because we are going from the minimum value which is 0, and we are approaching the max value, okay? And so the rate of change of flux, aka this value right here, is going to be the greatest, and therefore in this position, we are going to be producing the highest EMF, okay? Or the greatest EMF, I should say. And so if we were to take this, okay, and now we rotate it like so, okay? So now the coil is facing upwards like so, so it's going to be in this position right here. And so you can see here that the flux lines are passing through this coil at a maximum, right? We have the maximum area of our coil, and the flux lines are going through it. And so our flux is at a max. However, the rate of change of flux is at a minimum at this point, okay? So even though flux is max, the rate of change of flux is a minimum, and so therefore this value is a minimum, and so we have the smallest EMF produced. So therefore, max flux, but rate of change of flux is minimum, okay? Now, if we were to graph this, okay, we might think we have max voltage here, and this is over time. We might say we start at a max, okay, so we start at our max EMF produced, and then we go to 0, and then once the coil rotates again, okay, the coil is going to be in this position once more, and then you might say, oh, well, we're at a max again. However, this is not what happens. What actually happens is we form a sinusoid where we have negative voltage down here, and we actually form a graph that looks like this, okay? But why do we have negative voltage? Remember, the negative in this case is not lack of voltage, it's more so the direction is different, okay? So it's in the opposite direction to this voltage right here, okay? And so why is that? We can see that when we get to this point right here, if we use our Fleming right-hand rule, we know that our coil is rotating this way, okay? And so therefore, if we apply our right-hand rule to this side right here, this side is going to be moving up, right? If the coil is rotating this way, then this side has to move up and this side has to move down, okay? And so therefore, if we apply our Fleming right-hand rule, our magnetic field goes from north to south, okay? So therefore, our index finger is going to be pointing in that direction right there, okay? We want this side of the coil to be moving up, and so the force is going to be up, so our thumb is going to be up. And so as you can see, our current is going to be pointing in this direction right here, okay? And if we apply the right-hand rule to this side, our force will be going downwards, but our field is still from north to south. And as you can see, the current still goes in the same direction, okay? So that is the direction of our current in this scenario. To make this easier, we can label this side positive and this side negative, okay? So the current comes from the positive and then goes to the negative. If we were to take this exact scenario, copy it over, okay? However, let's say that the coil has rotated 180 degrees. And if the coil has rotated 180 degrees, the positive side will be over here and the negative side will be over here, okay? And so what that scenario is when we started from over here, we went up onto this position right here, which we can see over here, and then we rotated once more into this flat position once more, okay? So rotated 180 degrees. In the scenario, we are still going to be rotating in this direction right here, okay? And so therefore, our current is still going to be moving in this direction, okay? However, as you can see, our positive and negative terminals have flipped. And so therefore, we can see that our current has changed direction, alternating current. And so from this, we can say that every 180 degrees, our current changes direction, okay? And because our current is related to our EMF, we can say that every 180 degrees, our EMF changes direction, okay? And so if we have our graph, like I said before, we have our V and then we have our negative V. We start from max, then we go to a minimum value, okay? That is when our coils are in this position right here, okay? And then we rotate once more into this position right here, and that is this position, and our voltage is going to be in the opposite direction, but however, it's still going to be max, right? Still going to be max, but in the opposite direction. And then we rotate from this position back into this position, and so we are back to a minimum, and then we go back to a positive once more after 360 degrees of rotation. And like I said, because our current is related to our voltage or due to our voltage, our current is going to form the exact same shape like so, okay? However, it's important to note, just foreshadowing for future videos, our voltage and our current are in phase, okay? We can see that they're in phase in this case, only because this is a purely resistive circuit. In AC, if we start adding things like inductors and capacitors, the voltage and the current will be slightly out of phase, and we'll go through that in different videos, okay? So when we say that in New Zealand, NZ, we have 240 volt mains power supply, okay? So the power that comes out of your power sockets is 240 volts, and that is an AC current that has 50 hertz, okay? And so as we know, F is equal to 1 over T, and so therefore T is equal to 1 over F, and therefore our period is equal to 1 over 50, which is 0.02 seconds. And so therefore, if we have our voltage right here, every cycle is 0.02 seconds long, okay? And so that will be it for our first video on AC. See ya.